Yeah, I will. Before I do that, I just want to hype the Global Flood Partnership for a minute. For people who are just joining or not a part of this community, maybe Albert, you can drop in again, like the link to our website or how to join the listserv. But joining the listserv is the best way to kind of stay in touch with this community. And it's really a community of people who are making flood data, using flood data, trying to work together to actually mitigate and solve the problem of flooding costing lives and livelihood damage around the world. It's global. We collaborate. And we're also pretty democratic. We vote on our steering committee members. So if you're interested in being a part of our community, we would love to have you. We have annual meetings every year where we gather. I don't know, Albert, if we are allowed to announce, or you have announced when and where we're meeting. Can we say
You
it?
can say
Okay.
it, yes.
Okay. Jim Nelson is going to host us at Brigham Young University in Utah. I believe we're targeting the first or second week of August. So we'll be opening up registration soon. And we're really excited to hopefully see a lot of you there and do more of what we're doing now and just really sharing our knowledge and data sets with each other and talking to end users and figuring out how do we actually make data that people need and want to use and really do that co-production feedback loop between what people need and what scientists do. So that's what this community is all about, and we would love to have you be a part of it if you're into that too. And also thanks to Albert. This is a very female-friendly community, which remote sensing oftentimes isn't. Albert is always the person in the room saying, hey, could we get some women on this panel? Or I don't really see gender representation happening here. And that really, really matters. And for me, it's very fun to be on this like all women remote sensing and flood mapping panel, which I don't think has ever happened in my life. So we're a very inclusive community and we take that really seriously and would love to hear more of your thoughts. Okay. That's my hype for GFP, but Albert is graciously the voluntary chair. It's all volunteer run. This is a very bottom-up grassroots thing. If you want to get involved, please do. Anything
Thank you,
else you want
Beth.
to add on GFP, Albert? Before
No,
we
this is this
Okay,
is great. Thank you for advertising it. Yeah, super.
cool.
Um,
Okay. Yeah, GFP is no money, so we all just like try to participate together and, make a simple website and do what we can. But we think this space really matters. It's been a really generative space for me. Okay, my presentation is going to echo a lot of what Marella talked about, but some of our results are in contrast. So maybe we could have some good discussion about that, especially on the geospatial foundation models, which are really exciting, kind of bleeding edge space of remote sensing. And I think we're all trying to grapple with like, do geofoundational models help mapping or not? And is all this computation actually worth it? So I'll talk a little bit about that today. You can see my screen, right, Albert? Okay, cool.
yes.
Okay, cool. All right. So I'm just gonna talk about work we've been doing in my lab, which is called the Social Pixel Lab. We blend hydrology, social science, and remote sensing. And just like Morella's work, mostly work with actors outside of academia to figure out who needs a satellite-based flood map and what do you want to do with it. I actually saw on this call earlier Sazzad Hussain from the Bangladesh Flood Forecasting and Warning Center. That's one of the organizations that we've been collaborating with to co-produce flood mapping over the past couple of years. And I'll actually show some results from our collaboration in this presentation. Um, I also started a company about 10 years ago called Floodbase. And we work primarily with insurance companies to fund a type of insurance or to enable a type of insurance called parametric insurance, where insurance is paid out based on an index, in this case, inundated area from a flood map. I'm not going to talk about that work today, but I did at least want to kind of throw a paper citation up there for the main methods that Floodbase is using, which is combining the US National Water Model and stream gauges and rainfall with satellite-based remote sensing to create sort of these seamless time series maps of inundated area. For example, we're able to map, because of this fusion, flash flooding like what happened in Camp Mystic over the summer, which was on the cover of the New York Times this July. But if you want to learn more about sort of this method of fusing satellite data and hydrologic models, check out the paper that we published that Jonathan Frame led at the University of Alabama that sort of describes how to do it. And I'm not going to talk more about flood basin commercial applications today. I'm just going to dive right in to super technical remote sensing, since that's kind of what I figured this audience would be. Okay, so like Morella, in my lab, we do algorithm development to make flood maps from as many sensors as we can. So this is just a really overwhelming table of all of the sensors that we've been working with. ECTA use, for example, Rohit Mukherjee's Sentinel-1 algorithm development. We're mostly using convolutional neural nets, but we started to work more with foundation models and also long short-term memory networks and other types of AI. So I'll go into a little bit of that in this presentation. But we work with all types of sensors because that's what you got to do. As Morella said, if you want to catch floodwater, you have to use as many sensors as possible because it just moves so quickly. So first I'm going to show you our sort of hot off the press results on geofoundation models. I think in contrast with what Morella found, so we can have some good debate here. This paper is up on arXiv. It's submitted currently in review right now, but we just couldn't wait to release these results. So I'll pop the link in the chat, but it's also on these slides if you want to take a look. I'll talk about human-in-the-loop AI approaches and where we've been working in the Rio Grande Valley, Texas, through a project called Flujos, Flood Justice Utilizing Satellite Observation, and then a couple of other algorithm insights from results in our lab on a couple of different sensors. Okay, let's talk about geospatial foundational models first. So Morella previewed this a good deal, but I just want to highlight this kind of, I think, really key question of like, do they actually matter? Christopher Wren wrote this fantastic blog post called Geospatial Foundational Disappointments. And what you see essentially on this graph on the x-axis is flops. That's like computational energy kind of used for a model. So the bigger the flop, the more parameters it has. And on the other axis, the mean IOU difference, IOU is intersection over union. This is the most common accuracy metric in machine learning. 1 is a perfect IOU. So the mean IOU difference from a UNet, and Morella sort of talked about this. UNets have been sort of the really common deep learning algorithm for, I would say, the past 5 years, really dominating the remote sensing kind of flood mapping space. And what is sort of found is that you don't beat UNets. Like all of this insane computational effort in geospatial foundational models don't beat UNets, except maybe Terramind. Although Morella has run other experiments that actually fit in kind of to this blog post of like, maybe we're not beating UNets. So we wanted to dig into this much deeper in our lab. And as Morella talked about, we can't test every single one of these geospatial foundational models because there's like a new one every month, okay? There's been 58 released just in the past couple of years. However, and I put sort of, we made this table, this is in our paper, of different performance metrics of these models. That sort of the community kind of around this have started using to try to compare models to each other across many geospatial domains. One's called GeoBench, one is called Pangea. They do incorporate flood mapping as well, using Sentinel-1 Floods 11. But very few of them incorporate high resolution imagery. And we're also showing like the wide difference in millions of parameters and images that these models are trained on. So there's a lot. But we just took 3. So Morella tested Terramind. We actually tested different ones and got different results than her. And so maybe, yeah, this is sort of the bleeding edge of this science. Here's what we found. We found that we were able to get higher accuracy than a UNet on PlanetScope by quite a bit. barely anything on Sentinel-2. To me, a 3% increase in IOU is not that meaningful. But for Sentinel-1, huge accuracy increases of 23%. We found that Clay, the geospatial foundational model Clay, gave us the best results, but that the Privy model that NASA released was actually easier to use. So I don't have a comparison here with TerraMind, which Marilla used, and we also use different data to train our models. We used a data set I'll talk about later in the presentation that my lab developed called Flood Planet. And we actually used PlanetScope hand-labeled data sets to train and test the model that are coincident with Sentinel-1 and 2 imagery. So different data set, much larger though, in terms of images and probably higher quality, I would guess, because we're using PlanetScope, these sort of hand-labeled data sets at a much higher spatial resolution. So it's a much more difficult task. Well, we did find that I think was pretty compelling, was that foundational models achieve high accuracy with like very small amounts of training data. And this sort of like 2 or 5 images, by the time you have 5 images, you're already getting a 0.6 IOU with Clay is really amazing. And so I'm a little bit more optimistic than sort of the geospatial foundational disappointments blog post of like, I think there is something here. And we did find that they increased results. You can just like see it visually. Like this is a UNet result here. And all of the geospatial foundational models, and these are ground truth or hand label data here. All the geospatial foundational models that we tested look better. They've got much higher numbers than the UNet. Clay looks a little bit better. I would say in terms of the actual accuracy, it's pretty competitive compared to the other two geospatial foundational models. But it just looks a little bit crisper. And the reason for this is probably because it was trained on a lot more high resolution imagery. They trained, I think, Clay mostly on NAPE data, in addition to all of the other sensors. And so we're really seeing some advantages there when predicting on a higher resolution image. So yeah, that's all I'm going to say about this experiment. Please check out our paper on arXiv. We'd love to hear your feedback and comments on this really kind of bleeding edge of remote sensing that I think is a pretty exciting area. All right, I'm going to switch gears and talk about like really working with people and their lived experiences of where it floods and how satellite data can be used for flood justice and advocacy work. And I want to take you to the Rio Grande Valley, Texas. This is an area at the very, very southern tip of Texas along the US-Mexico border. There are thousands of colonias here. These are informal communities that were urbanized over time, often on former agricultural land. I don't have time to go into all of the legacy of colonialism and environmental racism that shaped flooding in this landscape. But needless to say, it chronically floods in this area. There's not sufficient drainage to remove floodwater. A lot of colonias are not officially incorporated into cities or municipal areas and don't receive the services that they deserve. But in addition to these chronic issues, there's also incredible community resistance and resilience, organizing and doing flood mitigation work. Lupe, La Unión del Pueblo Entero, for example, was able to successfully work with lawyers to sue FEMA to get flood relief to victims when they weren't getting a payout after Hurricane Dolly in 2008. But many of the homes, these are just kind of pictures of typical colonia homes and landscapes, are self-constructed slowly over time, and are really can really be affected by even small amounts of flooding because of the way that they're constructed. And what we've been doing in this region of South Texas with 5 community-based organizations is we built a history of all of these chronic floods. You can check out our flood database here. It's called Flujos. It's based on Sentinel-1 and PlanetScope for 13 events that these communities cared about. And we really built the tool in co-design with them to support their continued advocacy efforts to get more drainage to people, write more grants, make sure FEMA's giving disaster relief money to the folks who are affected, and so many other really important actions to mitigate floods in this community. It was most recently used in the flooding in March 2025 for aid, long-term recovery, and other advocacy efforts. But what's cool about this database isn't that it's just like some flood maps. It's how we did it with human in the loop approaches. And so I wanted to show this because I would encourage using this method in other places that you're working. What we did is we printed off our maps and then we spent time in colonias and with community-based organizations drawing on the maps, looking for errors, finding places, for example, this is just one example kind of in this purple hatch, where it floods across this whole colonia, but our flood mapping algorithm in blue really underestimated it. So we took and we digitized all of these lived flood experiences. I think we talked over 200 Colonia residents. Lucas Valere, my PhD student working there, this is his dissertation, would remember the exact number, but then digitized these experiences and used it to retrain the machine learning algorithm. This is called fine-tuning a convolutional neural network. And these are kind of what the results look like. Here in orange is the flood map from an event that happened, and kind of I want you to pay attention to these blue circled areas. Once we incorporated resident flood experiences, we started picking up more flooding that people had lived through, and it really made the model better. We got about a 10% increase in accuracy. But what's really important about this process wasn't just like the flood maps got better, but it's the process of working with people, having them like understand how maps are made and that their life is a part of the data that's created generates a type of trust and understanding that allows them to use the data and trust it. And that is probably more important, honestly, than just the accuracy increase that you get from a map. I was actually there just yesterday, and Monday and Tuesday of this week, and we were spending time with Arise Adelante, which is one of the community-based organizations we work with, who are supporting flood recovery for hundreds of families from the March 2025 flood. And so I just want to tell kind of one story about that neighborhood. So this colonia is called La Piñata. You can kind of see this irrigation canal from former agricultural lands that kind of curves around this community in South Texas. And we talked to one woman in a home there who talked about how horribly flooded her community was in March 2025. And we went back, looked at the data, and we could see on our satellite-based maps, like, yes, this area was flooded. And she said, you know, it was crazy. That's the biggest floods we've had in the past 10 years, which was interesting because the rain in March 2025 was just as high as the rain in many other flood years. And we went back and looked at the data in other large floods. There's actually been 4 federally declared disasters in this region just in the past 5 or 6 years. The big floods in 2018, 2019, 2020, we see, just like she told us, almost no flooding in her community, yet a lot of flooding just this past year. So this is really important. This sort of raises questions of like, why did this community flood this time? Is all of the rapid urbanization happening around McAllen, Texas, increasing drainage that's flowing through irrigation canals and flooding this community? Was the irrigation canal had some maintenance issues that the county needs to look into? So these sort of questions and this data can help these community-based organizations go and try to make change and demand maintenance and flood infrastructure for this location. So this is the type of work that we're doing, and the data we're producing is helping address. Okay, so that's flujos. I want to end with just a couple of algorithm insights from sensor fusion data sets and experiments that we've made in our lab. So switching gears a little bit, we know that radar satellites are really helpful in mapping floods when there's clouds. Both Ekta and Morella talked about this. This is just a regression from inundated area damage reported by the Bangladesh government and the inundated area we map with Sentinel-1. And you get a correlation here. With MODIS, we get no correlation between reported damage area and floods on the ground. Why? Clouds. This is a chronic problem in optical imagery. But even if you have this really nice radar data, we just don't have a very long time series. And if you're going to be pricing insurance contracts, which by the way, Bangladesh was the first country in the world to establish parametric insurance that pays farmers out based on satellite data. Big leader, as they always have been in climate adaptation, but it was based on a MODIS sensor. And so we wanted to develop something that was better than just, the current MODIS algorithm that was being used, but was longer in time than Sentinel-1. So what did we do? Use machine learning to fuse the two together. So I won't go into gory detail on this algorithm development. You can check out our paper, which was published in Earth Vision of CVPR about 2 years ago. But essentially what we did is we trained MODIS data on Sentinel-1 image captures over time and added in elevation data. The specific innovation here is adding in a long short-term memory network. These types of AI algorithms have become really popular in predicting stream gauge estimates in hydrology because it uses time series to predict the next like the next day's value. And so what LSTMs can do is look at sort of the flood wave that's happening in Bangladesh and fill in what's happening under the clouds in MODIS using both time, spatial context, and elevation to make a guess of where flooding might be. And it does a really good job. So we found that we got huge accuracy gains by using this LSTM than just CNN alone. And we produced a 20-year data set of historical flood mapping for every week in Bangladesh over the whole country over 20 years. And we found that even in really large flood events, it does a really, really great job capturing and sort of filling in clouds. And so much better than the global flood database algorithm, which we had previously worked on, which was just a thresholding based algorithm on MODIS. AI really, really gets, this is another paper from one of my students, Alex Saunders, really gets, like 50 to 60% better in terms of flood mapping than just a more traditional physically based algorithm on MODIS. And we've done some really cool things with this data. We've worked with epidemiologists who have re-estimated infant mortality flood-caused estimates in Bangladesh, and they're getting 45% higher numbers by using this better AI MODIS data than the global flood database that had previously been used to estimate infant mortality in Bangladesh. We've worked with economists who have used this data to really understand, does flood-tolerant rice seed varieties work in Bangladesh? How much is it increasing yields? And start to really pinpoint what is the amount of flooding at which we see these new types of seeds make a difference in yield? And when is there so much flooding, these seeds stop working? So these types of better time series data that really only are enabled by these new AI techniques give us new, really important insights in different socioeconomic domains. All right. I'm probably going to fly through a lot of this for time. And I think Alex Saunders and Jonathan Giesendonner want to give their own webinar about this with GFP maybe next year. But one of the things that we've developed most recently is a new VIIRS flood mapping algorithm. And we really saw the need for this. And I see Dan Slayback was also on this call, who's one of our partners at NASA, and Fritz Policelli, because there is no machine learning global flood mapping model. And so we wanted to make one for VIIRS. And this is very similar to what we did in our previous work in Bangladesh. We basically take VIIRS, sample Sentinel-2 water estimates from Dynamic World, and use that to train a UNet model on VIIRS and produce a fractional inundated area estimate at the pixel level. So this is just a map of all of the sampling we did. I think there's almost 100,000 chips where we sampled Sentinel-2 to then scale that up and retrain it on a Veer's algorithm all over the world, over every possible season. Lots of fancy sampling here. That will be in the paper that we have yet to submit. But what we found was that we got really, really good predictions compared to our labels. You can sort of see the difference map here where there's some under and over estimates, but by and large, we were able to capture a lot of the spatial patterns of Sentinel-2. And we compared that to NASA's existing near real-time algorithm on Veers to a Sentinel-1 image capture. And we can see that our algorithm does a much better job, even in these super cloudy conditions, estimating what's under cloud and cloud shadow. This is the NOAA GMU Veers algorithm. I think I saw William Straka on this call, and it outperforms that one as well. We see this consistently around the world, and just getting a much higher level of detail in inundated areas. We've heavily validated this, both on Dynamic World itself, but on 100 events from the Global Flood Database, other selected events that NOAA has run, and problem scenarios that Dan Slayback has identified, where it's really hard to make a good flood map, like in dark soil or under a volcanic shield. I don't have time to go into all the details, but we really did find the machine learning algorithm to significantly outperform both the NASA and the NOAA GMU Veers algorithm. So we're seeing these gains from machine learning, even if we do really extensive validation over a lot of different data sets. The last thing I'll end with, like Morella's lab, we've done all of this work generating validation data to train and test machine learning algorithms. And it is public. We would like for you to use it so you never have to go make validation data sets like we have. We have one on surface water, and we have one for 33 flood events around the world called Flood Planet. So check out those publications. We'd love for you to use this data if you're interested. What we have found using data sets like Flood Planet, which we use PlanetScope actually to generate our labels because we find we get much higher precision and accuracy, is that you can use a label from Flood Planet, which we've now released, to then train your Sentinel-1 or Sentinel-2 algorithm, and you will get a much more accurate result than if you use Sen1 Floods 11 or any data set that where you're just labeling on Sentinel-1 or 2, just because it's higher spatial resolution. So even if you don't have access to commercial imagery, you can use the labels we made from commercial imagery to test your algorithm and try to make it better. So in sum, how much is AI helping improve flood maps? Like generally, I would say we're kind of on the order of 10 to 25% increase in accuracy, which I think is substantial. We are seeing in our lab increases in accuracy from foundation models. Clay, Prithvi, and DOFA were the ones that we tested, but a lot more meaningful accuracy increases on PlanetScope and Sentinel-1 than on Sentinel-2. We really saw barely anything. So something to dig into there. We do see that incorporating lived flood experiences using AI helps increase accuracy about 10%. Adding in time series AI like LSTMs helps again by about 10%. And machine learning methods that we've been working with on Veers is really outcompeting previous methods by about 25%. And commercial data can give you another boost. We found about 15%. Over labeling data on Sentinel-1 and 2. So that's what I had for y'all. And happy to take a few questions at the end here.
Wow, super, Beth. That was a great presentation. Thank you so much. And like all the other presentations, actually, they're packed with so much information that I probably need to go back and look at the recordings again to capture it all. Let's see. There are a few questions in the chat. So to start off with a question from Mirella. Nice talk. I saw you used LMOU for the GFM work. Did you also use the recall?
I think we calculated that. Sarab Kaushik, who led this work in my lab, is on this call. I don't know if he has it. I can pull up the paper real quick and see if we have it in that table. We usually calculate IOU specificity, precision, but I don't
So,
have it like off the top of my head. But Sarab, maybe you do.
I mean, we have not compared explicitly with the recall because for segmentation tasks, that's what the standard metric is to compare different models. So, yeah, we did with the MOU, mean intersection of union.
Okay. Yeah.
Okay, awesome.
So
Yeah,
maybe,
Marilla pointed out how important that can be. So I appreciate the question, Marilla, for that.
yeah, maybe we should calculate that and then see how much our results differ. Although our results are on different validation data sets too. And so I feel like we should like rerun our experiments on the same data. And then maybe we can have a deeper conversation and collaborate in that way. It
True,
would be
but it
fun.
feels like we should all kind of as a community decide on what metrics to use so we can kind
Yeah,
of compare across sensors, metrics and such. So yeah, I think
totally.
yeah, that would be a good conversation to have.
Totally.
Very
Because
true.
it's hard to answer the question like, are GFMs helping when like you and I
Yeah,
are using different metrics and different data that we each both made in our labs.
yeah.
Before going to the second question of Marilla, I see Guy has his hand up, and I'm assuming, Guy, you can unmute yourself and ask the question.
Yeah, that's why I had it up because you left me the option to unmute. Maybe I can switch on my
Yes,
camera.
and that's my
Hey,
mistake, but I'm glad that I made that
yeah, that
mistake.
is a
Go ahead.
mistake. No, no, I'm sorry. I don't want to take other people's questions, but I had a very cool. I hope, Beth, you didn't go into this because otherwise, I did miss anything. I hope so. But it would be very interesting indeed. The UNet versus the foundation models, there's one
Mm,
advantage. The UNet is
mm,
very easy to use. Let's say,
totally.
let's say you like me, you don't know
Yes.
anything about
Yes.
AI/ML, and you have team members like that, but then I could even start a UNet, with some
Yes.
input channels, very easy. You go to Python, you have library. I always feel the foundation models requires a lot more background knowledge, and there's a cost
Yes.
of learning.
Yes.
Have you ever tried to do like a cost benefit analysis? So the benefit would be like the accuracy gain you have, but what's the cost of the UNet versus a foundational model? Like not only
Love.
computing, but also like cost of learning it, or
Mm.
how do you need to set up your machines? Is that different? Maybe it's a headache, and therefore even a 10% increase in accuracy is not meaningful. I don't know. I'm just putting it
No,
out there
that's
as
I love
food
this
for thought.
question, Guy. I'll give my take, and I'm sure Sarb and Marella have thoughts here as well, since they have experience with this. So I basically think for people who aren't super technical users, like just use a UNet. They're pretty good. They're like, we know they do a good job. I always say like units still slap. This is like a very Gen Z thing to say, but like they're good. Like add as a solid algorithm and you'll get a pretty good result.
Yeah.
Um, if you don't have a ton of computational power, they're super fast to run with inference. Like
Yeah,
units
exactly. Yeah.
great. I just wanted to present, like, as a scientist, thinking about what is the bleeding edge and direction we're
No,
going in
no, it's great.
algorithm
It's great. Yeah.
development.
Yeah.
Like, transformers are better. They are better than UNets. They do cost more computational power. It takes more to train them. And this is why foundation models matter. They really can help if you want to use transformers, like piggyback off somebody else's training data effort, and you do get a better result. But like you're saying, Guy, because it's the bleeding edge, can be really hard to run and set up and get to work really well.
Yeah.
And some are easier than others. Like we got better accuracy from Clay, but Sarah will tell you he'll just tell people to use Privly because it's so much easier. Like for PhD students
Yeah.
in our
Yeah.
lab,
Yeah.
we're just like, use Privly. Like it is not worth the 3% accuracy gain to like get Clay to work around the world. And so, yeah, I would say like, I think geospatial foundational models are sort of still in this realm of like scientific testing and really only useful for end users who are super technical. But my prediction is if we do this webinar in 3 years, we'll all be using transformers in
Oh, yeah,
geospatial.
probably. Yes. Yes, absolutely.
But
Yeah.
it's
Yeah. No,
just like
thank you. That
that
was,
that
yeah.
development I think is going to take some time, but I think that's where this field is for me so
Yeah.
obviously going. But I don't know, Sarab or Morella, if you want to comment on that.
Cool. Thank you. Thank you.
I mean,
And
I
I'm
guess.
heard about data centers too. Like, I don't know. I'm gonna stop. Morella, you go.
In space, you mean? No,
Yeah, so I
I
okay.
guess I
mean,
kind of echo what I said before. I think we've seen a lot of incremental improvements in accuracies, right? Like we see like 2%, 3% with this model, with this model. And so I think, and then we have a lot of benchmarking data sets. But as you've seen in this webinar, we don't use the same data sets and we don't use the same accuracy metrics. So as a user community, what would be useful to you? Would recall and precision be useful? Would IUU be useful? So I guess that would be a first thing to start with, and then the idea of really focusing on task specific applications. So instead of following the model that we followed with UNets and deep learning, where we just have tons of papers out there, and as a user you don't know which GFM to use, what data set to use, how to use it, like you're literally flooded with so many GFMs. I think the idea would be like, can we focus on task specific applications, such as in our case flood mapping, and then use the same data sets and use same accuracy metrics and decide, are we all converging onto one model, and then test those for particular applications. Like, is it urban floods that you're interested in? Is it dryland areas? Like, try to see what you're interested in and then work with users. I think that's my take on that for flood maps.
No, very good, Marilla. And so we're slightly going over time, and I'm fine with that. This is all recorded, so we will post, if that's fine with all the presenters, we will post this on the GFP website, hopefully by the end of this week. I want to continue with one or two other questions, but feel free to, go to your other meeting or do your other tasks. And that is, of course, if the presenters can stay a couple more minutes here. I have a question for Beth's presentation with humans in the loop. So you mentioned something like you did this great community effort where you mapped out flood events, even there where you didn't detect flood events at the first place. And then you went back, tweaked your algorithm, and were able to capture those flood events. But on top of that, you were also able to capture, I think if I understood your map correctly, also flood events in some other areas. So did you go back actually to those other areas, to the communities there, or that potentially are there, to see if those flood events were real, if they had happened, or if those were just artifacts kind of that showed up because you tweaked the algorithms and now it's getting more false positives, I guess.
yeah, great question. So we created a bunch of custom hand labeled data on Planet Scope that we use to compute accuracy. So when we redid the accuracy metrics, it would penalize the map if it was over predicting a bunch more because we added into new areas. And so I can tell you that in general, from the label data where we sampled across the region, the accuracy got better. But I don't know in specific places, like I didn't go back and visit other new places where we didn't have like human context and community-based organizations to see, did it flood on this date in that location, which is pretty hard to do. Like it's hard to even get people to recall, especially in a place like this where it chronically floods. Like, wait, did it flood here in 2018 but not 2019? People are like, dude, I don't know. So what we had to do is kind of work with community-based organizations that had records of this. So they had and this was a lot of like digging through Facebook pictures of forms that they had households fill out asking for aid of different years. And so there may be some more over prediction, but I think we're a little bit limited in what we can do. I feel like I can't fully answer your question of, did the over prediction overcompensate? Possibly, probably in some places, but it's hard to check.
Got you, thank you. And then I skipped over Marilla's second question. I'm not sure. I see Saurabh answered in the chat. I'm not sure if that's if that answer fully covers your question, Mirella, or not about the clay performance. If so, I see Antara has a question as well. We found in our internal tests with Kuro Siwo dataset on GFP that the foundation models always transferred better than the UNets to unseen flots. Did you also observe something similar?
Yes. Sarb answered that one, but yes, we did.
Oh, yes. Okay. I now
But
see.
the generalization
Okay,
is better. We did like you can see in the paper, I posted the link, but like leave one out cross validation. And that's kind of for us the best way to sort of test that. Withhold a region that you didn't train it on, and then you can kind of test on that. That's hopefully not spatially autocorrelated in any way to what the training data set saw.
Okay,
And like to
awesome.
expand on my answer to Morella, like I think, if a foundation model is trained on NAPE, which is a high resolution image, it's probably learning something about features in high resolution data that in our case we did see matter for something like PlanetScope, which Clay wasn't trained on. DOFA was trained, sorry, you'll have to remind me of the specifics. DOFA was not trained on NAPE. It was trained on, I want to say, some Chinese satellite. High
Something
resolution image.
Goffin 3.
Yeah, Goffin 3. And we found that that also worked really well in making predictions on PlanetScope. So I do think we have at least like evidence from 2 foundation models trained on high-res imagery that's not PlanetScope that transferred really well to PlanetScope. And what I think that tells us is like, yeah, you are getting something meaningful from foundation models that's really transferable across different types of images.
I'm gonna move to one more question and then we call it a day, I think. Molly's has a question about random forests. So random forests are an older or more traditional machine learning classification model, but they have been shown to perform well with less training data and less computational cost than UNets. Have you all compared results from random forest models with results from UNet or foundational models? And do you think there is still a space for random forest or forest detection modeling?
Marilla, do you want to take that one first? I'm sure we both have a take on this question.
Well, I definitely do. I definitely do, especially for noisy training data sets and for trying to generalize better. And we did show in some of the work that we did in Bangladesh in flooded rice paddies that random forest was better compared to a UNet when we had fewer and noisier labeled data sets. So I think it really depends on the amount of training and the quality of the training data that you have.
Yeah, I'm going to mostly concur with that, except to say that one thing we found when we did this experiment, it's called few shots experiments in machine learning with the foundation models, where we just took like 2 to 5 labels. They were incredibly good. And so I think this is what's cool about foundation models is with just a little bit of data, you can fine tune them. And my guess is that it would do better than a random forest. We saw it do much better than a UNet, but I haven't done, Molly, that exact experiment of geofoundation model to random forest. I've just done geofoundation model to UNet. But this sort of relates to, I think, Guy's earlier question is like, it kind of depends on like what's your time and your computational resources and who are you. Like a random forest is probably going to get you a really decent flood map, and you may not have the time or expertise to do a UNet or geofoundational model. And if you're getting good results, like, that's good enough. If you have much more time and you really care about that extra 5 or 10% accuracy, then I think it is worth investing in a UNet or a geofoundation model.
Awesome. Thank you so much for this explanation. Let's call it a day.